Welcome to the HVAC Engineering channel. This is a channel where we talk all things HVAC. We talk about engineering design, construction, equipment, systems, extensively tab, controls, and efficiency and performance of systems. These videos are intended to be a basic education to help you with your career. Today we're talking about how to specify building pressure testing. Now that may sound like a strange subject, but we have found in the industry that the architects and engineers don't really understand how to specify pressure testing. They'd like it to happen, but they don't understand what their job is into getting that to happen. So this is all about pressure testing and how you actually specify that. And it'll help you by educating the people you're working with. But before I do, I'd like to ask you a big favor. Would you please become a subscriber to the channel if you're not already? By hitting the subscribe button down below and the like button. The reason is, first of all, those cost nothing. There's no cost associated. It doesn't cost a dime. It's totally free. And once you subscribe, I will never bug you. I don't have that data anyway, but I wouldn't do that. But the reason is because Google uses those items to evaluate this video on their platform. And it's really important to me. So I'd really appreciate it if you do that. Okay, let's get started on how to specify building pressure. All right, so now we're going to talk about building pressurization and how you specify it so you actually get it done on the job. The whole building pressure testing assures a tight building which limits air leaks, which causes poor energy performance. No matter how well a building is designed, poor quality construction will still lead to poor performance. Testing is the only way to ensure that you have a high efficiency building. If you don't test, you'll never really know. So specification elements. 1, the architectural documents must specify whole building pressure testing. Now up here I talked about poor quality construction. And really what I mean is more about not understanding what quality construction is. It's not that it's poor quality, it's just wrong. So when it comes to building pressure, most buildings are built for aesthetics. I mean, built to work, of course. The structure has to be okay. But it's all inspected by an architect who does it by sight. What he can see is what he's going to punch. So basically, they build them, and they don't quite understand what air tightness really is. 2 pieces of sheetrock touching each other is not an air seal. And no matter how many times when we first start testing a general contractor, there's a lot of assumptions like that. Well, I can't see sunlight, so it must be a tight seal. Unfortunately, it takes a lot more than that. And it takes a few times when a contractor being tested who understands finally, okay, now I understand what I need to do. So architectural documents must specify the whole building pressure. You're not going to get it if you don't specify it. Must list the areas to be tested. Must provide square footage of test space and square footage of air barrier for each test space. So pass-fail requirements, so we know what passing is. If you don't specify pass-fail, then no matter how bad the building is, it passes. So you got to specify what the limit is. And that involves specifying the test pressure, what pressure we're going to test the building at, minimum acceptable leakage and CFM per square foot. And also back here, you need to specify what standard are we following. That's not as important as these two. These 2 things are absolutely critical. So the maximum size, so you know there is a size limitation. We cannot pressure test an 800,000 square foot airport terminal building. We just can't do it. There's no way to pump it up. There is a way. We actually developed a way to do it with building systems. But to do that, it has to be done during the design phase because we have to have a little more horsepower on return fans than we would normally have. But supply fans are plenty good to do the job, but return fans are not. So we need to work on that a little bit. So the size limitations by the size of test fans. How many fans do we have to have? The practical limit is 20 test fans or 7 doors. We all use calibrated test fans, which are about 6,000 CFM each. We can fit 3 of these in a door. We can fit 6 in a double door. But we don't use bigger fans. Some people have made bigger fans like 10 or 15 or 20,000 CFM fans on trailers. But they have a problem. One is you have to frame out an area, like part of a roll-up door for them to blow the air in. And two, they either need to be engine driven so that you have their own power source, or else you got to provide a power source for them. It normally be 480 volts. So that becomes expensive and difficult to do. So we don't see those being very effective. The biggest problem we have is, if you do 20 fans, you got to find 7 doors, a combination of double doors. And they need to be somewhat in the same area so you can control them together. The biggest problem is 2 fans per 20 amp receptacle. So basically, to do 20 fans, you need 10 circuits. That becomes problematic because if you have your fans all within a couple of areas, you have to have maybe 5 circuits per area, which normally there's only like 2 circuits per areas or 3 circuits per areas. And that's why we have long extension cords to be able to get our fans. What happens is the fans will overamp a 20 amp circuit if you have more than 2 fans. Doing multiple area tests are somewhat challenging if you're doing multiple areas because they don't really have an air barrier between them, and we'll talk about that in a little bit. So dividing walls must have air barriers, or if they don't, then we must pressurize both spaces so we don't get leakage between those 2 areas. So here's an example of why different buildings can have different test requirements. So I can't just give you a square footage limitation because it's all about air barrier. So if we have a certain air barrier, we need to know what that is. So here we have a 500 by 400 feet times 24 foot high, 1-story building. So that building would take 20 fans for a test flow of 110,000 CFM. But we have another building that's only 240 by 200 foot wide by 416 foot tall, a 26-story building, and it still would require 20 fans, test flow 110,000 CFM, and it's all about the air barrier. Now you realize this building would be a lot more square foot than this building, but the air barriers are the same, so you can test them to that kind of situation. So here's an example of doing 2 areas. We run into this a lot in military barracks buildings, which they have exit doors that exit outside, and there's no way to test the whole building. So they test every apartment by itself. And to do that, you have to test, if you want to test this area, and you have air barriers on this side, but you don't have any air barrier here, you have to put fans in both doors and blow them up to the same pressure. And then you let this one float at the pressure you're testing while you really test this one. And then if you got a whole bunch of them, you keep moving down the line. You have 3 fans, 1 on either side, and you keep testing in that fashion. It's a little cumbersome, but that is the way you do multiple spaces where you don't have an air barrier in between the spaces. So there are several test standards, mainly the ASTM E779 and ASTM E1827. These tests are similar, except this 779 test builds a curve on the testing from going from maximum pressure to minimum pressure. And this one selects 2 points, high pressure and a minimum pressure, and does a bunch of tests around those 2 points. Both of them give you the same output. I actually prefer this one better. I think it's easier to do, and I think it's more accurate. But this is the one that most people deal with, is the ASTM E779. Now, the problem with these 2 standards is they were developed some years ago, and they were developed for residential, not for commercial. So when you actually read these standards, you'll see some weird stuff like, how to deal with fireplaces and things we don't normally have in commercial buildings because they were dealing with residential. The process is the same, whether you're doing a residential or commercial, so that's why they've never changed them. But they still have some weird things in them because they're looking at residential. And then we have the U.S. Air Corps of Engineers, Army Corps of Engineers, and their standard has kind of become the de facto standard for the industry, because the Pentagon mandated that all Army buildings will have this test, and Air Force buildings. And some of them, Air Force kind of skips around a little bit, but the Army actually uses it on every single building. They all have the same test parameters pretty much. They just operate slightly different. The US ACE, there's also a NEB standard. There's some English standards out there. And the NEB standard is actually based upon these 2 standards. They just go into a lot more protocol than these do. So normal test pressure is from 60 PA to 75 PA. Even though we do these tests in inch pound. So in American units, we use a metric unit for pressure because it's whole numbers. So, 75 pascals is basically 0.301 inches of water column. So basically, it's much easier to deal with pascals, whole numbers. And the leakage rates range from 0.1 to 0.40, depending on the type of building and how leaky it's going to be, like how many doors it has, how many big doors it has, and that sort of thing. So that's a test leakage. Here's a table. I realize this table is sort of hard to read, but I'll show you. It's got a whole bunch of descriptions of the structure. It has kind of how many doors it has, and it has what the leakage rate is, and these have the test pressure rates normal. So if you look at this top one, this is a high mass critical environment conditions like concrete, poured concrete, steel frame roof structures with less than 6 doors. Now these are exterior doors, of course. Then we're talking about a 0.1 CFM leakage rate at a test pressure of 75 pascals. 0.1 is hard to get to. It's possible to get to 0.1 with a minimum frame building, with a red frame building, but you got to be really good at sealing and know what you're doing. Very few of those buildings that aren't high mass get to be 0.10. High mass standard environmental conditions with more than 6 doors would be 0.15 at 75 pascals. And then a medium mass building, which would be masonry walls, concrete structure, less than 6 doors would be 0.20. And then a medium standard building with more than 6 doors would be 0.25. And then a low mass building, which would be like a steel frame, metal frame wall, steel frame structure, standard conditions, less than 6 doors would be a 0.25. That would be standard office buildings would be 0.25 at 75 pascals. And then a low mass standard building with curtain walls, steel frame, and structure. Curtain walls tend to leak more than a standard wall. With more than 6 doors would be 0.30. And then industrial buildings, which would be low mass, like a metal building or steel stud building. This would apply to hangars, garages, anything that has lots of roll-up doors. With less than 6 roll-up doors would be 0.40 at 50 PA. And the reason less pressure is that because with these buildings that have so much leakage, it's really hard to get to pressure. So basically these are the limits, and what we normally say is critical spaces like laboratories or museums, anything that has critical indoor conditions, then we use a 0.1. Everything else would be 0.25, and we'll go to 0.4 on something that we know has so many garage doors, it just won't, many roll-up doors, it won't pass anything else. 4.0 is a lot of air. When is the test done? This is the problem. The test has to be done when everything's done. So we can't test until all the enclosure is done, including the door weather seals and floor sweeps. And normally floor sweeps are done last. They're done with hardware. But the contractor really needs it tested sooner to tell where the leaks are. Because if you don't discover that and you build this building and test it and find a bunch of leaks, they get really expensive to fix at this point in the game. So that's why we recommend that every building is going to be tested, the enclosure be commissioned, and it be commissioned to make sure that everywhere that could possibly be a leak is properly sealed. Okay, so we need to be fully commissioned. Testing mock-ups. A lot of architects think that testing their mock-up does some good, and it does almost no good, because when they build a mock-up, they build it the best you possibly can, but that doesn't actually translate into the construction process in the building. Now, mock-ups are done so the architect can say that looks good, that's what we want. And you can test one if you want to say water intrusions or something, but basically you still need to test the whole building. If you want energy as your goal, then you need to test the whole building. So how is air barriers calculated? Now, an architect, if he's using Revit, he can push a button and ask for the square footage of air barrier. And as long as it's defined on the drawings, it'll pull that square footage right out. So this is by definition of the standards, by the way, the area of the top story roofs for all occupied spaces, area of the bottom story floors. Now that's even if it's a slab on grade. And the reason for that is slabs on grade still leak. They leak at the wall jambs, they leak at floor drains, and they leak at any conduits that are leaving that space. So this still has a leakage rate. It just seems a little strange. The standards had it in there because they were dealing with residential buildings that had subfloors, which our commercial buildings don't have any subfloors, but that still has leakage that has to be accounted for. Area of the perimeter walls for all stories. So that perimeter walls that have air barriers, the roof has an air barrier, and the floor actually has an air barrier. So we go in there. Example, a 2-story building with 48,000 square foot for each floor that is 30 foot tall. So we'd have the roof, we'd have the floor, we'd have the 800 foot of perimeter times 30 feet is 26,400. And that totals 122,400 square feet. Now, that won't be that big a job because the leakage rate of 0.25 of the air barrier equals 122,400 times 0.25 equals 30,600 CFM that we would test at 75 pascals. And using 5,500 CFM per fan, that would make 6 fans. We'd have 6 fans on this job. So you can see that's not a total lot of fans, and still we're doing a pretty good sized building. So performing the test, enclosure, first we're going to inspect the building to make sure it's really enclosed. So we're going to enclose, make sure the construction is complete, that it's ready for testing. The door sweeps are installed and adjusted. The building is prepared for the test. So there's a bunch of setup things you got to do for a test. And by the way, one test is the building has to be unoccupied. You can't test unoccupied buildings. The reason is we have to have everything closed. I have tried many times to do an occupied building because the contractor could not do the test any other time. You only had a few workmen in the building doing trim or something, and we'd start a test, and all of a sudden someone would open a door. They said, well, I only open it for a few seconds, but it doesn't matter. It destroys the entire test. So you can't have an occupied building. And the best way is to lock the exterior doors so people can't come in and they can't go out. And that's best. There can be people in the building. It doesn't matter as long as they don't open something to the outside, like a window if they have operable windows or a door. So first thing we do, all HVAC systems are turned off. Now there is a specification out there by the U.S. government that asks for the building to be tested in 2 modes. One is building only mode, excluding the HVAC system, and another was including the HVAC system. And it's a pretty poor spec because it's very, very difficult to do a test without the HVAC system being involved. In other words, we like to test it like it's going to run. We want the air handlers in it. We want the ductwork in it. We want the building like it's actually going to operate. We don't need to see just the structure alone, because we need the whole thing. So we just seal the outsides of the air handlers, the louvers on the air handler, we seal that, and then we seal any louvers on the outside. So, but we want that to include. Normal openings are sealed, which includes exhaust fans, includes intake, outside air intakes, and any other normal area open. All gas appliances are turned off and the vents are sealed. And normally we do this by shutting the gas off to the building because we can't have any pilot lights on or anything like that. You do have to restart up the gas system once you're done. All interior doors and access doors are open. So we need to create a corridor between the inside of the building and the outside wall, because the outside wall is what we're really testing. So we need the air to be able to move freely between that. So we block open all the outside doors, and any access doors we open. And then on the very top floor, you have to have 10% of the ceiling tile removed. So that means I normally ask them to do that 10% of tile as a straight row down by the outside wall. So in case we have to do leak detesting, we can see the joint between the wall and the roof, because that's where most of the leakage occurs. So we want to be able to see that so our thermal cameras can see that. So then we install the test fans, and we perform a test fan under negative pressure first, and then we perform a test of positive pressure test second. And the reason we do that is because a negative test is always the best test. That's because it reinforces all the natural closure of the system. So if you have barometric dampers on exhaust fans or something, this will actually tighten them up. It'll make it worse. So it makes it a lot tighter building. Dampers on air handlers, it'll also tighten those up. So it's assisting the natural seal by sucking up the building. When you do a positive test, on the other hand, you're trying to blow all those things open. And normally when we have a seal failure, it's always under the positive test. So, the natural openings like wall louvers and outside air intakes and exhaust fan are all sealed, normally with carpet tack plastic. So you take that plastic wrap and you wrap it around the exhaust fan of the louver. And it works fairly well. If it's a big square louver, then you'll have to back it up with cardboard or something, because the sticky plastic does not work well at 75 pascals pressure again, so you need something to support it. If the test does not pass, then perform a leak testing to determine the areas of leakage. This is harder than you might think, but there's several ways to do it. One is to use a thermal imaging camera and to see if as long as you got a good temperature difference, you can seek that under negative tests, you can see the temperature intrusion into the space. You can use smoke. However, it needs to be a smoke candle or bung, because you can't do a smoke bomb because you can't see it. But on a stream, you can see it. Or hearing. You can hear the leaks. So ears are a good source of determination. I've also tested with a rotating vane anemometer. Go to doors, interior doors, and read the velocity through the door. And if you find a room that has a lot more wind blowing through the door, that's where the leaks are. So you spend a little bit more time doing inspections on that room to find the leakage on that room. This happens to be one of my forums. It's not typical of the industry, but they will all have some kind of test form. Nowadays, most of our instruments are automated, so we can actually do this all automated. But I still keep this manual form in case I have to do one manually. So what this involves this is the negative test up here. This is the positive test down here. This is the high pressure point. This test is for an 1827 form. This is for the low pressure, and when we're doing either a 997 or 779 or an 1827 test, we start off at 75 pascals and we end down at 25 pascals. So we want to have it right around 20 to 25 pascals at the minimum side. And on a E779 test, you take 10 different readings at different pressures to build a curve. On the 1827, we just take a bunch of readings around the 75 pascals and a bunch of readings around the 25 pascals, and that gives us the data. So down here is the job. This is the job criteria. This is the negative pressure. This is the positive pressure, and this is the average between the two. And so this lists all kinds of things. This lists the allowable CFM and the actual CFM of the leakage, and it also has in here the equivalent area. So if you added up all the leaks, what would be the square inches of the leaks, or sometimes the square footage of the leaks? And when you tell a building contractor that your leaks equal 10 square feet, it's a pretty big opening. So you have lots of leaks in the building, and that's how it helps. Now also my form has something that's a little different. Right down here and right down here, it has what would be the leakage at regular operating pressure. These leakage numbers are all at 75 pascals. What would it be down around 0.02 inches or 0.015 inches? And this will give you that actual CFM. Then all this data is the statistical analysis of the tests, because the test has to be within the 95 percentile for accuracy. And so there's a bunch of real fancy calculations up here doing the statistical analysis. And we look at the two factors here. One is the N factor and one is the constant factor, to tell us what the coefficient factor, and where they should be. So we know if they're within a certain range, within the 95 percentile. So that's basically it. This is what this is over here, is we read the pressure of every fan and we read the flow of every fan. And then this averages them up and we come up with an average flow and an average pressure, and that is used within the calculations. This is an output for the form. It just lists, this was the negative test, this is the positive test, this was the acceptance test, so this one didn't pass, as you can tell, is output. So how do you make a building pass? Well, there's some normal areas that leak, and we find them all the time. Transitions from wall to roof. That seam from the wall to the roof is really problematic and has lots of opportunity for leaks. Normally we like to see a foam seal with the fire caulk spray over the top of it, because the foam seal will take care of things you can't see. And it takes care of really little leaks and big leaks if you can't see them. Seal around beams and structural elements. Anytime you have a structural element that leaves the inside of a building through an outside wall, there's a real potential for a leak. The biggest problem here is that if you can't see it, if construction after that beam's installed covers it up and you can't see it, you can't tell if it's leaking or not. So this is why commissioning needs to be done, and anytime you see a beam penetrating a building, that has to be leak tested, or not tested, but leaked, sealed now. You can't wait, because when it gets sheetrock on the inside, you won't be able to see it. Transitions from floor to wall, that's another leak. That the plate should be sealed. I mean, many times you do a test, we see dirt pulled into the building through the plate, because then it doesn't have a seal. It should have plate seals. Exterior doors should all have weather seals and floor sweeps. Now, a floor sweep is just a brush, so it's not tight-fitting seal, but at least it impedes the flow a little bit. Windows, expansion joints are another big leakage area, especially on roofs. Roof expansion joints and roof flashings, they're all designed to be waterproof. No problem. They work great. But a lot of people never think about air-proof. We need them to be leak-tight, or else it's going to leak the building. And I've seen a lot of expansion joints that leak air like sieves, because they put bunting to cover up the hole, but they didn't ever make sure it was tight. So those all need to be packed tight with something that will be an air barrier, like insulation or the foam bunks that are in there tight, so there's no air can get around them. Wall and roof penetrations, obviously, seal around penetrations. On some buildings that have a lot of big conduits in them, we have to make sure that the conduit's actually silicone sealed after the wire is placed in the conduit, so the conduit doesn't leak from the space. And the bottom line is, once a contractor has built several buildings that have passed pressure tests, the experience tells them how to build a building, and they will be able to build tight buildings. So as you work with a contractor, you'll notice his leak rates get less and less and less, because he's understanding more and more and more how to build a tight building. So that's it. Pretty short course today. I hope you enjoyed that. And don't forget to subscribe and like. And I hope you have a great day, and I'll catch you on the next one. Thank you.